Imagine you are hiding behind the living room couch, trying to peek around the corner into the kitchen without giving yourself away. You cannot see what's happening because of the basic mechanics of vision. We rely entirely on light to see the world, and light operates under a restrictive law called rectilinear propagation. Rectilinear propagation means that light refuses to bend around obstacles on its own. It only travels in perfectly straight lines. If a couch or a wall is in the way, the light stops. But you can manipulate this rule by placing strategic barriers with tiny holes or bouncy mirrored surfaces in its path. You can force light to go exactly where you want. Understanding how to work with light's straight line rule allows you to build instruments that specifically redirect your vision. Take a look at the layout for a simple pinhole camera. Notice what is missing. There are no glass lenses. It is just a light-proof box with a single tiny hole, an aperture on one side, and a blank screen on the other. This diagram shows light's path. Since light travels in straight lines, rays from the tree's top pass through the pinhole, hitting the bottom of the screen. Simultaneously, rays from the base cross at the pinhole, landing at the top. Because those straight lines cross at the aperture, the resulting picture is completely upside down or inverted. And because this picture is physically projected onto the screen surface, it is a real image. This creates an engineering trade-off. A tiny hole restricts incoming light, creating a sharp but dark image. A larger hole lets in more light, but the image becomes fuzzy because straight rays overlap. The pinhole camera proves you do not need complex curved glass to capture a picture. You just need a single hole to organize scattered straight lines of light into a coherent image. An upside-down image isn't always helpful. If you need to see over a high wall or peek above the surface of the ocean, you need to detour the light while keeping the picture right side up. To solve this, submarine crews relied on the periscope. By looking into a vertical shaft, they could observe surface threats while staying submerged. During World War I, soldiers in trenches used the same tool to monitor the battlefield without exposing themselves to danger. The mechanism follows a Z-shaped path. A horizontal light ray hits a 45-degree mirror, reflecting 90 degrees down the tube. It then strikes a second bottom mirror, reflecting 90 degrees horizontally into the eye, creating an upright virtual image. By angling two bouncy surfaces, the periscope detours light's straight path around solid obstacles while keeping the view correctly oriented. Mirrors can also be arranged into geometric traps that turn simple reflections into symmetrical patterns. A kaleidoscope uses 3 mirrors arranged in a long triangle to reflect a handful of colorful beads into complex designs. The mirrors meet at 60-degree angles, creating multiple reflections. This is where the image in the first mirror acts as the object for the second, causing reflections to multiply. As you rotate the tube, the colorful pieces tumble. The angled mirrors force that random movement into repeating, symmetrical mandalas. Artists and designers use this reflection system to generate new ideas for intricate fabrics, wallpapers, and geometric patterns. The kaleidoscope uses this triangular mirror arrangement to turn a few pieces of colored glass into an infinite series of symmetrical designs. One tool flips the world, another detours your vision around a wall, and a third reflects fragments into a pattern. Yet every one of these effects relies on the same unchanging law. Light only travels in straight lines. This limitation is the foundation of optical technology. The lenses inside your smartphone and the massive mirrors inside space telescopes are all built around this rule. You can see the evidence anywhere. The sharp edges of a traditional shadow puppet or a reflection in a calm puddle prove that light has a perfectly straight path. Look around your room. Every color and shadow you see is the result of millions of invisible, perfectly straight lines of light reaching your eyes.